Okay, so put this in for defining limits. And remember, the limit's always read on the y-axis. Defining limits formally with epsilons sorry, there's just one L there. With epsilons and deltas. Okay, the epsilons are the Greek letter that look like this. Okay, and the deltas, the lowercase delta. We already worked with the uppercase delta. The uppercase delta was like this on the rise over run. This is the lowercase delta. Okay. First, let's go through the definition, and then I'll go through some examples. The limit of f of x as x approaches x sub 0, okay, equals L. Now, we've written that with the limit notation. Okay, it might be written this way: the limit of f of x as x approaches x sub 0 equals, and they're using L to represent the limit. The limit is L if the following holds. Given any radius epsilon greater than 0, that means your epsilon's positive, about L, there exists, and in the upper level math, they're going to use, for there exists, they're going to use a backwards E. For there exists a radius delta greater than 0 about x sub 0. Okay, there exists a radius delta greater than 0. That's just telling you your delta is positive. About your x sub 0. Remember, your x sub 0 was that value on the x-axis that they gave you to begin with, such that, okay, in upper level math, they're going to use this symbol, the backwards epsilon, for such that, for all, and for all, they're going to use the upside down A for all x's. And the absolute value of x minus x sub 0, show that as an absolute value. And instead of reading that as the absolute value represents distance. What that's really saying is the distance from our x to our x sub 0 is less than delta and greater than 0. Okay, the distance from x to x sub 0 is less than delta and greater than 0. That part implies the distance from our function to our limit is less than epsilon. Okay? And that's if it's really a limit, okay? Those things have to be true. This part has to imply this part. Okay? Okay, now, what does that mean picture-wise? Okay, it makes more sense if you look at a picture. Okay? Okay. Draw a coordinate axis. Pretty good size so you can see it. Okay, and we've done lines and we've done curves. For this one, we're just going to do a line. Say I had a function with a line. Okay, And what we did in this section, in this last section, was they gave us, pick a point, they gave us an x value, and they called that x sub 0. Okay? And if you come over across from that point, that y value is actually the limit. Okay? And they did it both ways. They gave you an interval on the x, okay? And let's say pick the same interval, about the same distance from the x on both sides, okay? This distance right in here is our delta on both sides of x sub 0. This is our delta. But this is x sub 0, this x sub 0, this is actually x sub 0 plus delta, and this one would be x sub 0 minus delta. Okay? But the distance in between each one of those, this little part, this is delta on each one. So add delta and subtract delta. Okay? Then if you go across from each one of those points, this is the limit minus epsilon. And if you come over here, this one is the limit plus epsilon. Now, you've already worked problems like this. You know, when we just talked about one, you know, if the one that Shaylee asked, it was like, what, within 0.2 of 0.4, something like that. The 0.4 was the limit. The 0.2, 0.4 plus 0.2. The 0.2 was what? The 0.2 was actually the epsilon, right? Okay, they had numbers in there. Okay, and the whole idea is that if this really is a limit, okay, then no matter what what delta you choose down here, I can find an epsilon up here that's going to put it within that interval on the y-axis. You could say, okay, Cooper could say, okay, I'm going to use 0.1, okay, for my delta down here. And then I would be able to find an interval here. Chloe could say, oh no, I'm going to use 0.01. I'm going to go smaller. Okay, so we would narrow that gap down. We would narrow the interval. And then I would narrow this interval on the y-axis. If it really is a limit, okay, if it really is a limit, I will always be able to come up with an interval on the y-axis. Okay? Okay, so let's look at an example with numbers now. Okay? Okay, so let's say, as an example, we did one similar to this the other day. Let's say I give you the f of x is 3x plus 1. And I'm doing it with a line, but you can do it with curves. Okay? The difference, before I would have said, okay, if I said the limit of 3x plus 1 as x approaches 2. In the problems before, I would have said find the limit. Okay, but on this section, they're going to give you the limit. Okay, we just substitute 2 in. 3 times 2 is 6, plus 1 is 7. Okay, now they want you to actually show that that is a limit. Okay, so, and I'm going to give you, let's do a picture of this. And it would go through at plus 1, and the slope is 3. Okay, I'm not going to do an exact graph. Just do a, okay, that's the y equals 3x plus 1. And pick a point up here. This is not an exact graph. Okay, let's say this x value is 2. Okay, and this limit then is 7. Okay, now let's say I want this within 0.1 of 7, and I want to know what's this interval about the x. Okay, so similar to what we did on today's homework, we're going to do it with specific numbers first. Okay, then this would be 7 plus 0.1. This would be 7 minus 0.1. Okay, so what I want to know is, what's this interval on the x-axis that puts all these y values? When I say all these y values, I'm talking all the y values on that line. All those y values need to be inside that interval. Okay? Okay, so one way to do that, okay, would be to take, I can do it more than one way. I can take the function, f of x, and force that in between the 7 plus 0.1 and the 7 minus 0.1. Okay? And then my function would be 3x plus 1 is less than, now go ahead and combine it, 7.1, and this would be 6.9. Okay, and remember, split that up into 2. 6.9 is less than 3x plus 1, and it's an and statement, it's a combined inequality. 3x plus 1 is less than 7.1. And if you subtract 1 on both sides, so we get 3x is greater than 5.9. Okay, and then divide that out, what do you get? Do it on your calculator. 1.9. Does it round exactly? 19666 repeating? Okay, and that's repeating. Okay, and then subtract 1. We'd have 3x is less than 6.1. Divide by 3, and x is less than 2.0333 repeating. Okay? Okay. Now, you have to look, if I rounded this to 3 decimal places, if I round to 1.66, okay, if I round that to a 7, okay, if I round that to a 7, okay, I would be on the right side of that, right? If I'm on the right side, does that put that y value inside there? Yes. Okay, so this would be okay to be 1.967. Okay, the other one was 2.0333. If I round that down to 2.033, that would put me on the left side. Does that put that y, if I'm on the left side here, does that put the y value inside here? Yes. So this is 2.033. Okay? Now, if the author said, find the delta, okay, how can I find this distance in here? Okay, 2 minus 1.9. All you do is subtract. Okay, subtract that. What do you get? Yep, 0.033. How do I find this one? Which one's the bigger one? This one or this one? Yeah, so you want the 2.033 minus 2, the 0.033, right? So this would work for our delta, right? This would be okay. Our delta, now, look up here for a minute. Our delta would be okay to be less than or equal to 0.033, right? Less than or equal to 0.033. If I went smaller than 0.033, let's say if I went smaller, wouldn't I be in here? And wouldn't that put those y values still in that interval? Yeah, same thing if I went over here smaller. I'm still inside this interval if I go smaller, right? So if they asked you to find a delta, you'd go ahead and subtract and say, as long as I choose my delta to be less than or equal to, then I'm inside this interval which puts these y values inside this interval. Okay? And that's where it would be like if Amy said, I'm picking my delta to be 0.031, okay? Then you'd be inside this interval. All those y values are inside, okay? Gunnar says, oh no, I'm going 0.02, okay? And you would be inside, right? Okay? Okay, so on this one, our delta, and you're going to write it out like that inequality, okay? Delta is less than or equal to 0.033. And then that 7 really is the limit at x equals 2. Okay? You can just go smaller and smaller. Okay, now there are 3 equivalent statements. I basically solved this by the graphing, and I also solved it by using an inequality. I forced, and if I look at this, this is actually the f of x, and this is actually, what was the 7? That was the limit, right? At x approaches the limit, at x approaches, this is the limit plus, what's the 0.1? That was my epsilon, and then less than the limit minus epsilon. There's a reason I didn't have you actually subtract and add those last section. I wanted you to keep it in the form, the limit plus epsilon, the limit minus epsilon. That's the inequality statement that you can use to solve these. Okay? You force the function in between the limit plus epsilon and the limit minus epsilon. Okay, there's 3 equivalent statements. Okay, put these in your notes. One of them is to use absolute value. And instead of just reading it absolute value, think of it as distance. Okay, it's the distance from the function f of x to the limit. Okay, that's the y value to the limit. Okay, is less than epsilon. Okay, think of it as distance. And if you look up here, you're really looking at the distance in here from the limit, and the epsilon, this is the epsilon, this each little part here. Okay? Each part in here is your epsilon. Okay? So the distance between the function and the limit has to be less than epsilon to keep it inside that interval. Okay? Okay, the second statement we just did, the f of x is less than the limit plus epsilon and the limit minus epsilon. Okay, this one is the inequality statement. And you will have to use that one a bunch. But a lot of these you will use the absolute value statement. But on that absolute value statement, you're really thinking distance. Because it's the distance from the f of x minus the limit. Okay, and then the third one is to say the f of x, the function, is in the interval and the interval is the limit minus epsilon and the limit plus epsilon. Okay, so absolute value, inequalities, and intervals. Okay. Now we've just gone through an example where they're working with specific numbers. Okay. Now I want to take you through like a problem you will get in the book. Okay. This is actually one out of the book, page 154, example 1. And you need to study directions. Okay, what they ask for is show that the limit of f of x minus 3 as x approaches 1 is 2. Now, they will either say the word show that, or they will say the words prove. Prove that it is the limit. Okay? For the majority of them, I would use the absolute value. So I'm going to use the f of x, or the distance from the function to the limit, is less than epsilon. Might make those a little bit darker. Absolute value. Okay, now you have to go back up here. What's the 5x minus 3? That is the function. You might want to label that. That is the f of x. What's the 2? That is the limit. What's the x? What's the 1? Now you have to go back to the notes. Go back to the notes. What was in this? Go back up to this. What's the 1? X sub 0, right? Okay, and we're starting with this in the problem. What we want to get down to is this, okay? You want to stop on these problems when you get to x minus x sub 0, okay? That's where you stop. Okay, so go back to the problem. This is actually the x sub 0, okay? So sub in the absolute value of 5x minus 3 minus the limit is 2. Okay, and for what we're doing, do we have an epsilon in there? Did I give you one? No. So that's just in general. That stays. Okay. Okay, so if we simplify, okay, we would have the absolute value of 5x minus 5 is less than epsilon. What's in common? 5. Now, don't be too quick. Take that 5, it's still inside. Okay? Now, what's the absolute value of 5? Absolute value of 5 is 5, so I can take that outside. We still have the absolute value of x minus 1. Okay, is less than epsilon. And now get that x minus 1 by itself. Maybe I better show that in 2 steps. Okay, now take the and divide by 5 on both sides. Okay, and the 5's would reduce, and I'd have the absolute value of x minus 1. That's really saying the distance from x to x sub 0 is less than epsilon over 5. Okay? And that's when you stop. When you get down to x minus x sub 0, okay, is less than something. Okay, in this case, it's epsilon over 5. And your answer, everybody look up here for a minute. As long as you choose, you got to finish this off with an answer. As long as you choose your delta to be less than or equal to whatever we got here, epsilon over 5, it will always work to put those y values inside that interval on the y-axis. Okay? So, let's say I chose a specific epsilon. Sometimes the author's just going to leave it like that. Say you find the delta, and you'd say delta is less than or equal to epsilon. But sometimes the author is going to give you an epsilon. Okay, so let's say let epsilon be, on this one, let epsilon equal 0.01 as an example. Okay, so then you would go back up here and say sub in 0.01 divided by 5. Okay, so when you divide that out, okay, when you divide that out, so 0.01, do that on your calculator. 0.01 divided by 5, what do you get? 0.002. Okay, so if I picked a specific epsilon to be 0.01, then that specific delta is going to be 0.002. Now you could go back. Let's go back and check it. Okay, let's check this specific example. Okay, So if I said epsilon's 0.01, okay, so go back up here. If we're looking at our graph, we're going to have something that goes through like this. At x is 1, y is 2. So if I said x was 1 here, go across, my limit would be 2. Okay, and if I said, I'm checking this answer, if I said my epsilon was 0.01, right? So it would be 2 plus 0.01, 2 minus 0.01. And this is going to be, you would really have to blow this up a little bit. It's going to come across here. And what I want to know is, what do I think these x values should be? Yeah, I'd have 1.002, and this one would be what? 0.9998, right? Okay. Now check it on your calculator. Okay. Put it in on the calculator. Let's try it. If I figured that right. So graph the equation, graph the beginning function was 5x. What do you need? Okay, so graph the beginning function, 5x minus 3. And then graph the 2 plus 0.01 and y sub 2. And the 2 minus 0.01 and y sub 3. Now it's going to be so small that you're not going to be able to see it. So you're going to have to do a zoom in, or zoom box. I would probably do a zoom in, okay, because you can't see those. Okay, so do a zoom in, get that cursor close. Where's it at? There it is. Get that cursor close to that point of intersection. Okay, and then press enter. You're going to have to do that several times until you can actually see those two lines, until you can find the point of intersection. Now you're starting to see them. Get the cursor close. Okay, as soon as you see the two lines, now do second function calculate intersect. Do it on, you want the line and the horizontal line. Okay, and there's my 0.998, okay? And the other one should end up to be 1.002. So, what would my delta here be? My delta is 0.002, and as long as I choose it to be less than that, okay, then I'm always going to be inside this interval, okay? I could say, okay, go back and make my epsilon 0.0001. Then I'm going to make my delta smaller. All I have to do is substitute it back in. Okay? Okay. So now you really have two ways so far. And a lot of these proofs, that's what they're going to start with. They're going to start with the absolute value. Okay? Let me finish. They're going to start with that absolute value. Where do you stop? You stop when you get down to x minus x sub 0. Okay, and then choose your delta to be less than or equal to whatever you've got, and it'll always work. Okay, so you've got inequalities and absolute values so far. Okay.